Assalamualaikum and good morning. So we will start with the name of Allah. In the name of Allah, the most gracious, most merciful. So I'm going to recite some verses of the Quran that is related to the session today. وَإِذْ قَالَ رَبُّكَ لِلْمَلَائِكَةِ إِنِّي جَاعِلٌ فِي الْأَرْضِ خَلِيفَةً وَإِذْ قَالَ رَبُّكَ لِلْمَلَائِكَةِ إِنِّي جَاعِلٌ فِي الْأَرْضِ خَلِيفَةً. And the ayat goes on. So I will explain you what happens that. That is the event that has been occurred when Allah says to the angels that I'm going to make a subordinate on the earth, on the planet Earth. And the angels replied that that human is going to shed blood and corruption on the planet Earth while we praise you all the time. So Allah replied that you don't know what I know. And then Allah has put some objects in the front of angels. And he asked the angels, can you name those objects? And the angel says, no, we cannot. Because we don't know, we only know what you have taught us. And then Allah has put the same objects in the front of Adam. And Adam has told all the name of the objects. So how we are resonating this verse is the intelligence. It was not only the creation of the human, it was a creation of the cognition, of the intelligence. And from where we start to the development of different technologies, and now we have moved towards the artificial intelligence. And even AI has built upon the natural intelligence. So today the session is about emerging technologies for next generation healthcare. So in session one, we are going to see what are the challenges we are having in healthcare and having the use case of Alzheimer. So what is Alzheimer basically? We are going to see that. And Alzheimer as a diagnostic case. So we are going to see that how Alzheimer can be detected using AI, how we can use AI to detect Alzheimer, especially in the case of spontaneous speech, acoustic signals, like the articulation of our speech, how we can use it to detect, diagnose the AI, Alzheimer's. And in the second session, after the team, we are going to discuss what is the way forward and what are the things, what are those multimodalities, for example, how we can integrate it so that we can move towards the next generation of healthcare. And in that session, Dr. Malia is going to tell you what is the global health concern related to Alzheimer, what are the clinical diagnostics and MRI and genetics. So genetical analysis is going to be discussed. So in both of the session, we are going to share Jupyter notebook so that you can have some hands-on because we are going to extract some feature related to acoustics and genetics as well. So let's move forward. So healthcare challenges is like a tip of the iceberg, and we are having a lot of things downside submerged in the ocean or in the sea, where we are having delayed diagnosis. Because when we cannot diagnose a disease, we cannot try to treat it. And then late diagnosis leads to expensive treatments because these type of treatments, for example, cognitive impairment, they are having expensive treatments and surgical procedures. And then on the third level, we are having limited remote access towards the remote population where the people cannot have even the internet access. So how we can move towards them so that we can diagnose those diseases at the early stage. And on the fourth level, we are having context aware. Like the systems that we have developed, they do not have, like, for example, a lot of data available. So we cannot converse towards what are basically the reasons. For example, what are the mutations in the genetics or the genotyping and how they have been expressed in the phenotype. So one of the phenotype what we are discussing today is the acoustic signal, like the articulation of the speech, how we can express our words, how we can talk to each other, how we can describe objects. That was started from the event that I have told you that Allah has put the objects in front of Adam and Adam articulated them. He told what is what. So acoustic signals. We are having the motivation why we are developing these AI healthcare systems because there is a use case of in China. There is an AI hospital that has been built up as an autonomous hospital. There are no medical care staff. There are no healthcare givers that can help you in diagnosis of the treatments. So you go there, and all of the machines are there. They are AI driven. So whatever the test you are doing it, whatever the reports coming out of those systems, they are AI autonomous systems or maybe agentic systems. So that is our motivation. That is where we want to move to. And then the second use case is affordable healthcare solution, because there is a rising demand. And with the rising demand in the developing countries like Pakistan, India, Bangladesh, and in the first world like China, we are having a very rapid increase in the aging population. So when the age population is increasing, we are having more old age related diseases like Alzheimer, which is a neurodegenerative disorder that has happened inside your brain. So acoustic screening of Alzheimer genotyping, that is the analysis that we get from the DNA extracts. And what is the way forward? So this is what we are going to discuss today in a panel discussion and with you. So early detection of Alzheimer, like as we have discussed earlier, that we want to detect early disease because we want to treat it so that we cannot have a cost effective solution. So early detection of Alzheimer, what we are proposing here, or the state of the art is proposing, that when we observe the speech of an individual, we can have some features from that speech that can be indicative of the cognitive decline. For example, if a person is talking and he has given a task to describe a picture, and he's taking a lot of time to describe those elements, and he's recalling the vocabulary again and again, and he's, for example, he's taking more pauses, he's thinking. So that is the indicative of the impairment that is going on inside the brain. So that's why we are going to detect those changes that is happening inside the brain through the early detection of Alzheimer. This is the only point. Okay, this is. And the whole genome, on the other level, we are not just only talking about the acoustic signals, we are going to talk about the genetics, like what is happening on the molecular level, like inside the body, what is happening there. So we are going to discuss whole genome. Dr. Maria is going to shed more light on it. And then in integration of these modalities. So the first modality we are going to discuss is acoustic signals, that is the spontaneous speech and the feature extracted from that speech. And second one is the genetic analysis or the data coming from your genes. And on the third level, we are going to see what can be the way forward if we try to integrate them. So what conclusion we can draw from the integration of these two modalities. So that is on the panel discussion. So goal of the project is, like, we are going to have remote diagnostics. So what we are trying to build upon is a software that is uh, an executable file that can be run on your desktop and can be on your app. Okay. So it solves the problem of remote population or the remote diagnostics. So that software is running 24/7 inside your mobile app or inside your web. And it is continuously changing or recording the voice that you are working with and extracting all of the audio features so that it can converge towards some indication of your cognitive level. And the same thing goes with the genetics as well. So that is an affordable and simple solution, because to download an app from a Google app or the Apple Store is very easy and it's free. So we have designed like the integration as a low clinical resource settings as well. Like for example, you can argue that these type of models that are working with the multimodalities, they can be having a high weight on the edge devices, for example. So we on the next level, what we are going to uh, extract the features from those modalities so that we can build upon the importance score of those features. And only those features can be reflected in the model so that we can have a lightweight model that can be deployed on edge computing. And the personalized treatment. So the voice signals and genetics data as well. So this is like a personal data. And you know that every person has individual phenotypes, like the observable traits, they are having different. For example, the eye color, the hair color, the skin color, and even your voice, the intensity of the voice, the frequency of your voice, and spectral features, and on the linguistic levels as well. There are different features of the individuals. So that's why when we integrate acoustic signals and the genetics data, it becomes a personalized treatment for each individual. So the treatment plans for each of the individual will be different because they are having different features extracted from their phenotypes. That is, in this case, is acoustic signals. So when you are having a differentiation in those features, you are going to be reflected with the different treatment plans. So that's why personalized treatment. So such type of models can lead to remote diagnostics, affordable and simple, and personalized treatment. So these are the three goals that we are working. So now coming back to the nature, the human brain. So we are having 6 parts here, and each of the brain part is handling different levels of cognition, different level of motors. So the thing is that what we want to conclude from this figure is like in case of Alzheimer, what happens on the cell level is we are having, you can say that abnormal proteins that accumulate in different parts of the brain. So, for example, if the protein has been accumulated in one of the temporal lobe, so what are those functions or the expressive traits are going to be compromised are understanding the language, behavior, memory, and hearing. So that protein accumulation hit these cognitive levels of the brain. So at each part where that accumulation or integration of the protein will happen, you are going to be affected by the cognitive levels of these brains. So what actually happens in the case of Alzheimer is like on the left side, there is a normal neuron. So this is a cell. We are having a neuron over there. And this is how these are the fibers that they try to communicate with them. So these are basically the electrical signals that is happening on the cell level. And these electrical signals, they try to communicate with each other. So what happens in the Alzheimer is that we are having two types of proteins that I have told you, tangles and plaques. So the tangles, they build inside the cell. Or you can say that these are the unwanted material that has been created inside the cell, and that is corrupting your signal. So your signal is deteriorating. And on the other side, on the cell level, when the individual cells are communicating with each other, you are having plaques. That is another protein that has been accumulated between the cells. So you cannot communicate inside a cell. You cannot send a signal outside the cell. And even if some of the energy has been sent, they are going to be blocked by these plaques. And what happened on the molecular level, they become dead. And when they become dead, your brain starts shrinking. And if that part of the brain represents, like, for example, the memory, hippocampus, your memory is going to be affected. And you are going to have challenges in planning daily tasks. The regular activities will be disturbed. So this is how Alzheimer works. So this is like what is Alzheimer is on the neurons level. So it's like a progressive neurological disorder that causes memory loss, cognitive decline and behavior changes. That is, we are not having a planning abilities to do it. So why acoustic signals? I have told you earlier that acoustic signal is like the phenotype that we discuss and we express to communicate with each other. When we try to explain some object, when we try to communicate with each other, and in the moment of intelligence, when Adam told the names of those objects, that was the articulation of the thoughts and the articulation of the spontaneous speech that we try to do it. So why we do with acoustic signals, we extract speech patterns and acoustic features and cognitive markers. And we try to analyze them that what are those values of these features that are differentiating factor between a normal person and a healthy control. And that is basically the representation of one of the uh, protein that has been accumulated in a certain part of your brain. So that is going to be reflected by these speech patterns. So there are a lot of work going on these that you can see in the research gap. What we have found is like the available data sets, they are in English language. So there is no availability of like Urdu data set because we are working in Pakistan because Alzheimer share, Dr. Malia is going to shed light on it that there are 11.5% rate of the death that has been caused by the Alzheimer. So there is a significant percentage that has affected the Pakistani population. So we do not have Urdu data set. So there are English data sets, there are German data sets, there are Spanish data sets, French data sets, but we have scarcity in terms of Urdu, and we are trying to gather those data as well. And so what is the methodology? So once we have the data, so what is the methodology that we are going to follow through? So maybe a hardware development. So there is a microcontroller that is like a EPS, and we are having a small microphone. So we just need this to record a voice, just a mic. Or for example, if you want to send those data to a server, so the EPS is going to help us in connecting with the local server or the server on the internet. So they are going to send all of those data connecting from our server so that we can have a data acquisition from the server. And what other things that we can do with this hardware is like we can conduct clinical trials. So it's like a tiny device that you can take it anywhere, or you can put it in a remote location and you can have the data acquisition from there. So once the data acquisition has been done, we can start doing the analysis. But before that, because the data was not present, so what we did, we have they acquired the data from the Pittsburgh University. So there were experiments going on the spontaneous speech that they have given a task. For example, in this picture, they have a cookie theft image. So there is a boy who is trying to catch the cookies from a kitchen cupboard cabinet, and that is a scene that has been taken from, let's say, uh, their literature books, and all of them are having tradition of telling these or narrating these stories in a general population in the Pittsburgh. So they have given this task to a large number of population, and they try to get the the transcripts of the language and the acoustic signal. So they are trying to check the memory. How is the memory of these patients, and how is the recall of these patients, and how they can well describe this picture. So that is a you say that is a clinical trial that has been done on this spooky theft picture that you can do it. So basically, these are all the English speaking volunteers, or maybe there are some volunteers from the Spanish population as well. And what they have gathered so far is like healthy controls, um, and Alzheimer's patients, they are with the same number. So 123 numbers for each category, so that they should know that what are those normal features coming from a healthy control, and what are the features that is coming from a patient of dementia who has Alzheimer. So we are doing the training of our model on these data sets right now. Okay, so what we are trying to do is like we can have clinical trials for Urdu, and we try to integrate the features extracted from the Urdu speech, and then we try to compare with the Spanish or with the English speeches. Okay, now the software and model implementation. Once we are done with the data acquisition, we are moving towards the software and machine learning models. So that is the workflow that we have followed. Like, what is the EDA? We explore the data, their demographics, for example, and then we pre-process the data. We try to, because these are the raw audio files, dot wave files or dot MP3 files. So we cannot have convergence towards what machine learning is going to get from those raw files. Right? So what we do the pre-processing, and in the pre-processing, we try to clean the noise, and then we try to extract the features, and then we select the features, and then we have the proposed framework. So EDA, in EDA, if you see, like we try to differentiate different features of the acoustic speech, and we try to differentiate between the dementia bank and the speeches that we have collected from the Urdu population. So we are having, a lot of resemblance in the speech. Why? Your question should be that why there, because one individual is having a Urdu language and the one is having an English language, or one we can have a Spanish language. But when we analyze those speeches or the acoustic signal on the feature levels, they are having the same characteristics, because we are not just following the linguistics, we are following the inner features of the voice. For example, intensity, loudness, and spectral features. And we can have like what is the frequency of those features. So these are the features that are differentiable if we even do the across language analysis. So this is like whatever the language the individual is speaking, we are having the same set of features that we have extracted from the spontaneous speech. So pre-processing involves like this is an audio raw form. So we are having a x-axis, we are having a time and amplitude as well. And for example, if we are having 100 individuals and we have taken samples from these 100 individuals, the time may not having the same. The time duration of each file may not be the same. So we try to pre-process or remove the noise from those raw files, and we try to normalize them in terms of their time duration, so that we can have x-axis and y-axis of all the individuals. They should reflect the same thing. And one more thing, what we are trying to do, because in this spontaneous speech data, we are having two persons. So one is the clinical doctor and the other one is the individual. So we try to segment the whole raw file, because we do not try to train our model on the voice of the clinical doctor. So we only want to interpret or train the model on the voice signals of the individual. So that is one of the pre-processing we are having, that we try to segment the data. So this is how we segment, like we try to recognize manually or with the software that what are those segments where the individual is speaking, not the clinical doctor. So we try to extract only the voice from the individual. So that is the segmentation. So segmentation is the significant step of the pre-processing. So we try to segment the voice signals. And what we do, for example, we try to overlap. So there is a metric that we can use, that we do not want to, lose the information of that individual. So we try to overlap the voice so that we can overlap the different segments. So we can have like a analysis that from 0 to 50 or 50 to 100, we try to analyze what overlap we can use so that we cannot lose the data. So once we are done with those 100 or 123 speech signals, we are having segments. So we are having like 6,600 segments from the Alzheimer individuals and uh, approximately 4,800 or 4,900 segments from the healthy controls. And what we can do, because again, that is a machine learning or AI is data hungry models. So what we can do, this data is scarce. So what we can do, we can have like augmentation, data augmentation. So what we can do, we can have like pitch variations, playback variations, and we can introduce in the same individuals, and then we augment the data so that we can enhance the data in terms of the numbers. Okay, so one of the important thing is like as we have seen, and we are going to see again, the raw audio file is having a spectrogram, for example. Let's move to that. Come back. Okay, so if you plot those spectrograms from the voices that has been plotted like this, so you are having a time on the x-axis and you are having a frequency on the y-axis. So these are the spectrograms from two different individuals. One is healthy control and the one is Alzheimer or dementia patient. So in this case, the machine learning model does not understand what is happening. Okay, so you are having just information like time and the frequency. So what we try to do, we try to extract features from these spectrograms. And those features has been extracted using the EGMaps library that is used for feature extraction. So there are maybe n number of features, maybe 100 of features. When you put a raw file inside the the EGMaps gives you n number of features. And obviously, all of those features, they are not of interest. So you need to see the importance of each feature, what type of features you want to analyze, and even in the subcategory of those important features, you need to extract the features. So in this analysis, what we are trying to come up with is like three features from the spontaneous speech, that is intensity, spectral features, and the frequency features. And on the linguistic level, we are going to see in the hands-on that we are going to analyze like what is the filler words used by an individual, what are the pause ratio. So these are two features that is coming from the linguistic and the spontaneous speech that we are going to see in this session. So if we sum up like how we are going to provide the remote diagnostic, how we are going to run these models on the edge computing, and how we are going to make it sure that this is a lightweight model. So this is the methodology that we have followed through. So on the feature selection level, we are having a spectrogram from where we perform the data labeling. Okay, this voice sample is coming from the healthy control. This voice sample is coming from the Alzheimer. So that is the, maybe you can apply a manual labeling or you can just apply clustering on that. And then we are having audio segmentation that we have talked about, because there may be noise, there may be different people speaking in that duration. So you need to perform the segmentation so that you can recognize what is that individual or patient that you are talking about. And then comes the part of the EG maps, which is a library that is a standardized library that is used to extract features from the spontaneous speech, and we extract the features. So once we are done, because I have told you that we are having n number of features, so we cannot work on all of the features because some features are not of the demand. So what is true for the traditional programming, that is garbage in, garbage out, is true for AI programming as well. So you do not have to give a lot of bulk of data to the machine learning model. You have to work with the important features only, so that your model is trained on the relevant information, not on the irrelevant information. So that is the feature selection, that what is the importance of each feature. And then we perform the modeling with respect to different machine learning models. And we are going to see what machine learning model we have used. And then we are having the model selection. So we are having complexity, error metrics, precision, and accuracy. So these are some of the metrics that we have used, and why we have used, for example, complexity. So the complexity can be translated in many forms. So one of the form that we are considering is like the CPU time, and towards the lightweight development of the model, we are considering like the weight of the model in terms of the model training and in terms of the storage that has been occupied by that model when it is deployed on the server. So that is the why we have used complexity, because we need to deploy this model on the consumer end. So that is like a consumer end. That is an app that we have used, a mobile app or a web app. We are going to use it. This is what we have reflected, and then we have an API controller, because this model that we have deployed is going to be on the server, and we are going to make inference from this model using API controller, because maybe when the model is deployed on internet or on the web app, there may be hundred of users trying to access this model. So there should be some API controller, how we need to manage those and number of users so that they can be transparently managed by the databases and by the AI service as well with respect to the database. So this is like the two phases we are having: model training and selection, model deployment that is on the server, and the client server interaction. And these three things are reflected on our goals. And what was our goal? Like the remote diagnostic, and that has been happened with the consumer app. We are going to we can deploy it anywhere. And then we are having cost-effective solution in terms of complexity. That is the CPU time, and in terms of the storage as well. So that's why we are having model deployment. That's the second phase. And then we are having client server interaction that has happened with the application. So these phases of the proposed framework is aligned with the goals that we have talked about before. So now, with this methodology, what we have obtained from the results are here. So let's talk about like intensity related features of the spontaneous speech. So this is a radar chart that has differentiated like the Alzheimer patients and the healthy controls. So the dotted line represents the values of the intensity related features coming from a patient who is having detected the Alzheimer on the clinical stage. And healthy controls, they has been represented by an orange line. So if you sum up all of these features, so that is basically the loudness. So in the earlier stage of my speech, I have told you that the spontaneous speech should be well articulated, and that is the differentiation between the Alzheimer patient and the healthy control. So we have extracted the same feature that reflects the sound or the loudness of that phenotype, the behavior that the person exhibit with respect to the physiological changes in the body. So that is the loudness. So if we sum up all of these loudness features and we try to differentiate between Alzheimer and healthy control, so we are having a difference of 36.2%. That is a lot of huge difference. Like the loudness of a healthy control is more, and the loudness of a Alzheimer patient is less. So this is what the radar chart is telling us. So it means that on intensity level, when an Alzheimer patient describes some task, he is having a low intensity in the voice because of the cognitive decline or the disorder that have been happened on the neurological level. So if we like closely look what is happening here. So loudness mean, if we try to take up the mean of the loudness, so we are having the values here from for Alzheimer is 0.29, 0.38. 50th percentile of the loudness, we are having 0.25, 0.32. Mean falling slope, we are having 1.83, 2.97. Loudness percentile range, 0.36. Shimmer means, so 1.3. So if we sum up the whole of this graph, it tells you that the intensity related values of the feature, they should be higher. for a healthy control. And if the intensity related feature values they are having lower from a range, that means that is the uh, indicative of the cognitive impairment that has been happened in the brain due to maybe the integration of the amyloid or the beta protein that we have talked about inside the neurological cell. So the second feature is like the spectral features. And these spectral features represent the quality of the voice. Like, for example, if a person is talking, they are trying to make some, they are having a blur in their voice, or they are trying to catch up with the voice and the breath as well. They are having some, indication, or they are having a mismatch in the synchronization. So, what type of voice coming out? So, that is actually the quality of the voice that has been reflected here. So, there is an index which is Hammerberg index, which is the indicative of the spectral features. And if this feature is having an indicative of the cognitive level, then we are having the spectral features like this. And if you sum up like the whole of the values coming from the spectral features, we see that we are having a decline of minus or 4.1% decline in the speech of the Alzheimer patient. So this is the indication that healthy controls are having more spectral efficiency, and the Alzheimer patients they are having less efficiency in representing the Hamburg index. And then we are having a third intensity, that is the frequency level. So on the frequency level as well, we are having a decline here, which is 15.6%. And the other one is the jitter. Jitter is another feature inside the frequency domain that is indicative of the decline. So in that case as well, we are having a 1.5% increase in the Alzheimer patient. So it means that if the jitter is higher, so it means that person is having a impairment. So in healthy control, jitter is less. Okay, so on these features, because that was very difficult to train our models on the spectrograms because they were having a time and the frequency. So these were only two things that we can train our model on. So that's why what we did, we tried to extract the features from the raw file, and we get into uh, train the models on those features. Like for example, in this case that we have discussed three features: intensity, spectral, and the frequency. So we have trained our model on these features. That how is the reflective of these features in terms of Alzheimer and the healthy controls. And we are having these number of machine learning models that we have trained our model on. If you remember, we talk about like the segmentation and non-segmented data. So initially we are having a segmented data, like these black circles, they are indicative of the segmented data that we have performed the segmentation on. And then we are having a non-segmented data. So there is a clear difference that if we do not perform the segmentation or the pre-processing of our data, there is a clear indicative or that the model is not going to perform well, because there is noise. There are number of people coming from the background or from the clinical doctors. So there is not a one single person that is indicated. So it means that there is a clear difference that you need to perform a segmentation on your data. And on the other hand, if we see that random forest is performing good, CNN is a bit good, and then RNN. So it is the indicator of the thing that maybe random forest is well enough to capture the complexities that is coming from the intensity, spectral, or the frequency related feature of the voice. And that settles well to bring out the complexities of those spontaneous speeches. And CNN as well, because CNN is not performing so well compared to the random forest, because maybe CNN needs more data, and we were having a very less data in that case, just 123 individuals. And then we have extracted like around 6,600 uh, uh, intensity or spectral related features from there. So maybe CNN needs more data to converge towards a higher accuracy or higher error rate. So that is the confusion matrix of the random forest because that is outperforming model in our case. So we were having like 343. So that is the indicative of the true positive labels that we have discussed. Like whatever the true case is, like it was healthy individual or the Alzheimer demented patient, it has truly reflected it and predicted it. But we are having some errors as well, like 28%, like 28 of the individuals that were actually Alzheimer demented, we have, our model has classified them as healthy controls, and 93 is as having a true negative, false negatives. So this is the error that we are having, and we can try to improve them with respect to augmentation or getting more data. Or maybe we can try to introduce multimodalities. That's what we have talked about, like the genetics of the same person, so that we can have multiple inferences from a single person, so that we can our model can predict more accurately in terms of those modalities. And then in terms of the deployment, so these are the results that we have tested across cloud and across the edge devices. For the cloud, we have used state-of-the-art cloud, that is AWS, Amazon Web Services, and maybe I think, yes, Amazon Web Services, not the Microsoft Azure. And on the edge computing device, we are having a Raspberry Pi. So what we have produced from there, the model that we have done, the random forest, we have deployed it on the hardware. And we have tried to infer, like on the real-time network, what is the inference rate. So if you try to see, and we have not just used a single library to implement the model, we are having a scikit-learn and we are having a TensorFlow as well. So there is a differentiation between these two models, and we have performed a number of client-server interaction to perform the inference. Like we are recording the voice and sending it to the server, and the server is providing us the inference that what is the cognitive level, yes or no. So that inference is reaches up to, for example, in this case, which is the case of Raspberry Pi and Alzheimer non-segmented data. So it shows like if the data is not segmented, we are going to have a more inference time as well. That is on the testing level, when the client is giving you the data and trying to infer from the model, that is taking more time. And in terms of segmented data, so you are having less number of time, maybe up to 40 seconds or maybe up to 20 seconds. And sometimes under the 10 seconds, you are getting the input. So this is like the deployment part of our methodology, that what we have produced so far with the spontaneous speech, we have tried to deploy it on the edge devices and on the cloud as well. Okay, so that is the end of the theoretical part, and now we are moving towards the hands-on session. We are going to see the linguistic features and how we can try to calculate the importance of those features and how we can train the model on it. And after that, we are going to discuss the way forward. And Dr. Ajmal is going to discuss like what is the way forward from here and how we can take the diagnosis, let's say the diagnosis of Alzheimer's from there on. Okay, let's have a break for 5 minutes and then we resume. Okay, so now we are moving towards the tutorial session that is going to be the hands-on. So we can share this notebook with you later, or if because we do not have like a sharing point right now, so we cannot share it right now. So we can share it later on, and you can perform it. It's very simple. So what we are trying to do, we have talked about like the three features that was coming from the spontaneous speed. That was intensity, spectral features, and the frequency related features. But now we do not discuss about the linguistic features. So in this hands-on, we are going to see what are those linguistic features that can add on to the generalizability of the model, or we can predict well towards the cognitive level of the individuals. So in this tutorial, we are going to see what are those features that we have termed as linguistic features. So it is a little bit slow, right? Okay. So these are the three features that we are using it as a linguistic feature. So one is like the mean pause duration, speech rate, and the filler words. So speech pause duration is like an individual when he is talking or he is describing a task, as we have discussed, like a cookie theft picture, when it has given a task by the clinical that you have to describe this. And while describing that task, he's taking pauses. Maybe because he's recalling some words, recalling the vocabulary, or trying to think about what is the scenario that has been depicted in a picture. So, whatever the reason is, he's trying to take pauses. That is the duration of speaking a next word. So, that has been represented as the mean pause duration. And the second feature, that is a linguistic feature, is the speech rate. So speech rate is like, for example, if we are talking about 1 minute or 10-second duration or 20-second duration. So how many words he's trying to speak in a certain time. So that is the speech rate. And that is the speech rate of different groups. For example, the first three are from the healthy controls. So if you see, like the healthy controls, they try to speak more words. They are having more vocabulary to describe or describe a depicted picture, or when they are trying to express their feelings. So they are having a more speech rate. Filler words. So the filler words are like we can also say they are the stop words, like commas and when you are trying to discuss the transcripts. So you are having HMM. So they are reflecting that a person is trying to think or recalling some words or recalling the vocabulary or recalling a scenario that has been happened in the past. So that is the filler words. So if you see that we are having more filler words when the patient is having a dementia. So one is reflected that he has been diagnosed as a dementia patient. So they are having more usage of those filler words. So these three features, they are the reflective of the linguistic property of the individual. So this is how we can differentiate between a healthy, controlled, and an Alzheimer patient on the linguistic features. So with respect to EDA, so if we try to plot with like a box plot, we are having these groups like 0 representing the group that is having a healthy control individual, and 1 is representing that is having a person who is having cognitive decline. So if we measure the mean pause duration, so it is having a lot of uh, pauses in his speech. And same is the case with the speech rate. When the person is healthy control, he's trying to use more words. That is the whole description of the features that we have talked about earlier. And the filler words, if you see like the person who is having healthy cognitive, it is having less usage of those filler words. So this is like a simple EDA that we have performed on the data, and they are having data pre-processing techniques that we have talked about earlier. So they are here for your hands-on experience. And obviously, we have used like the 80-20 or 70-30 ratio for the training and testing of the models. And when it come up, because the random forest was like that, we have seen that the random forest was performing so well on our spontaneous speech. So we have used the same data on the linguistic features as well. And we have come up with the error matrix as shown here. So we are having good matrices because it's a very small data set and we are having a good accuracy over here. So this is like a confusion matrix we are having. So it is performing very well. So all of those healthy controls, they have been detected by very well in generalizability of the model. And all of those cases that having Alzheimer is rightly identified. So one of the things that we have talked about, because when we are uh, taking the raw files, we are having n number of features, and we do not want to put the garbage in our model. Because if we train the model on the irrelevant data, that is not going to be generalized. So what we do, we try to see what are those important features. So we try to score them. So that is the visualizing the importance of the features. So for example, in this case, we are having three features that are the three linguistic features. And we try to analyze the importance by scoring them. So what is coming up here? Okay, so the third one is the filler words. Okay, so here. So on x-axis, we are having an importance of these features, and on the y-axis, we are having the features. So out of these three features, the importance of the feature that has more significant is the pause duration. So the pause duration, like for example, out of these three features, the pause feature or the pause duration, the feature coming from the linguistic modality, it says that the pause duration is a very significant feature if you try to differentiate between an Alzheimer patient and the healthy control. And the second one is like the speech rate. How number of words, what are those number of words that have been thrown in a second or in 10 seconds or whatever the interval that you are trying to uh, determine. And the filler words, they are having on the third level. So this is like the importance of the features coming from, because right now we are just having three features, but when you extract it from the EG Maps library or the library that you are trying to work with, you may be having n number of features, maybe 100, thousands, 2,000. So in that case, you need to determine what are those features that are important for my model. And then you will come up with the scoring of this model, and then you are going to train your model. So that was about the hands-on related to the acoustic features. And now we are moving towards the way forward. Like this is the established state of the art that we are working on the acoustic speech diagnosis of the Alzheimer patients. And we are trying to extract the linguistic and the frequency related features as well. But as we have seen, our model was not so performing well. It was having the accuracy related to 90% or 95%, and we want to increase it. So, what is the way forward? We are going to discuss in our panel discussion, and Dr. Ajmal is going to shed some light on it. So, over to Dr. Ajmal, and let me share the presentation.